Yeah. Yeah. Hi, welcome back. It's now time for our invited to talk, um, and we're going to welcome Sarah back to HAX. Very happy to do so. So Sarah's an assistant professor at Colorado State University. His core research interests include designing human-aware decision-making systems to generate behaviors that align with human expectations. He completed his PhD at Arizona State University, where his doctoral dissertation received one of the 2022 Dean's Dissertation Awards from IRA Fulton Schools of Engineering, and was an honorable mention last year at ICAPS. His research has been published in various premier research conferences, including AAAI, AMAS, ICAPS, ICML, ICLR, ICRA, HCI, IROS, and HRI. And NeurIPS and journals like AIJ and in the AI magazine. He's presented tutorials on his research at various forums and is the lead author of a Morgan Claypool monograph on explainable human AI interactions. He was selected as a DARPA Rising Scholar for 2022 and a highlighted new faculty at HAXP23. So I'm very excited to hear what he's got to say, and thanks.
Thank you so much. So as Ellen mentioned, my name is Sharad, and it's a bit of a homecoming for me. And I would like to take this opportunity to talk about human-aware AI, at least the way I see it. So without much further ado, okay, to start with, I keep getting told that I'm living through a golden age in AI. So in fact, New York Times says maybe the AI is just too smart. I keep being told the AI is going to keep doing more and more wonderful things. In fact, there were 2 labor strikes in US where AI was an important factor that led to that strike. Somebody in fact told me that we are in an exponential curve in advancement, so there's no point in looking at any other problems anymore. In fact, there is a good solution to it. All you need to do is just give more and more money to Sam Altman, and he's just going to solve all the problems, right? So this is an example of a ChatGPT wrapper that was, deployed in Australian World War I memorial. Somebody could jailbreak it to think it's Jar Jar Binks, right? But given enough money to Sam Altman, all of this is going to be solved. So the question is that it? Is it time to wrap up ICAPS? Are we going to just switch off the lights and be on our way, right? So I would like to think no, because if you were to look at the landscape of the current AI boom or the AI excitement, one thing we don't see are AI systems that are being deployed in mission critical or safety critical settings. That is not to say AI has not been deployed in those settings, right? We have a rich history within ICAPS, within traditional AI, or what people might say good old-fashioned AI, right? Where these things have been deployed into extremely important settings, right? Here are some of the examples, right? The person who is helping with drilling the oil, one of the examples I put in, is sitting in the back. So we know all these examples, right? But I do want to say that even though they are extremely successful, one thing we do see is most of these applications involve people who've been specifically trained to use these systems, right? In some sense, they are people who are used to the idiosyncrasies of the system and know how to use this, right? So in some sense, in addition to building these systems, we are also training people who are somehow AI aware, right? They know how to use these systems. So we are still far from the dreams or the hopes that all the sci-fi novels told me, right? I'm far from a world where I can trust a robot to take care of my aging parents back in a village back in India, right? We are not there yet. At best, we have chatbots who I'm worried might radicalize my parents, right? Or tell them to add glue to pizzas or eat stones. If you guys don't get the reference, please look up what Google summary AI system told people to do, right? So what's missing? obviously, there are advances to be made within a lot of these hard problems that are still missing from our current solution or current tool set. But I also believe that solving these problems require us to rethink how AI should be designed, right? And to kind of describe what I mean by that, just let's take a look at how if we were to teach an AI course or an introduction to AI course, or if you were taking an introduction to AI course, this is how AI systems would be introduced. So like, this is one of the basic architectures you would have. You would have an AI system that's acting on its own in this, completely like empty world, that it's figuring out what actions to do, and it's like getting some sense, like, information from the world and figuring out what next action to do is. I would like to argue that this is, in some sense, an incorrect view of the world. There are no AI systems that are deployed in isolation. They're always artifacts meant to be used by people. As such, at the heart, AI is always a multi-agent problem. And we always have to take into account how these AI systems' actions are going to impact the people it's going to interact with. What are people's beliefs about the AI system? What do they want from these AI systems? These need to be taken into account from the beginning. And when I talk about human-aware AI, it's this inclusion of these considerations into the design of AI systems. We need to take into account, all these considerations when we are designing algorithms, when the AI systems are coming up with its actions. So this is kind of a high-level, more philosophical slide of what I mean by human-aware AI. But to be, more concrete, let's look at what I would call the most basic human-aware AI setting. So this is a dyadic setting. That means there's only two agents. Okay, there's a human and there's an AI system. So AI system is the actor. So the AI system has a model of the world. It has some decision-making algorithm that's using that model to come up with its decision. There is a human who's looking at the AI system, looking at how the AI system is acting, and they have their own model of the world, something I'll call MRH. And they're trying to figure out, given the current task, how should the AI act? And this is what I would call pi star MRH, right? So in some sense, whenever the human is looking at the AI system, it's trying to figure out, or in some sense, forming expectations about what the right course of action is. In this basic human-aware AI setting, one of the fundamental questions that come up is what happened when there's a disagreement between what the AI system should do and what the human expects the AI system to do. And if you look at most of the problems in human-AI interaction, we see that at the heart of this problem, this mismatch in expectations keep showing up. So what I want to do is take this basic formulation of human-aware AI and try to see how this formulation would help us understand many aspects of human-AI interaction. Part of one thing I'll talk about is explainability. How do you frame explainability in these terms? Then I'll talk about advisability. That is the ability of the users to correctly instruct a system to do what they want. Okay. And if the time allows me, I would also like to talk about how this framework also allows us to capture trust and allow us to create assistive and deceptive systems, right? All of them grounded in this basic mathematical framework, right? So I want to, in some sense, convince you that this framing is rich enough to capture many diverse aspects of human AI interaction. Okay, so before we go in to some of these modeling aspects, I talked about this difference in expectation. So that's kind of a large kind of a more abstract view of the things. But as we go through each of these different aspects, I want to touch back on this asymmetry, and I want to talk about these three dimensions of this asymmetry. First one we'll talk about is difference between task knowledge, which is basically what the AI system knows and what the human thinks the AI system knows. This is one of the dimensions in which this difference in expectation arises. Then there is a difference in inferential capabilities, which is basically, given the same knowledge, what kind of inferences would the AI system make versus what kind of inferences would the human come up with. And then there is the difference in vocabulary, which is basically the terms that the AI system is going to use to represent its world versus the terms that the human is going to use to represent this world. Okay, and we are going to see how these dimensions, in some sense, affect these different modeling aspects. Okay, so this is the basic outline of the talk. I'm going to focus on two aspects. One of the thing, like the bulk of the talk is going to focus on two aspects, which is basically explainability, and that's been some of the earlier work I've been working on, which is basically, how do you make sense of the problem of generating explanation using this framework? Then I want to focus on advisability and specifically focus on this problem called value alignment, which is kind of a loaded term, and I'll clarify what I mean by value alignment. And I'm going to talk about some of the newer works I've been doing to use this framework to both understand and come up with methods that resolve value alignment. Okay? And then if you have time, we'll also go into things like, what does trust mean in this case? Well, how do we create assistive systems? How do we create deceptive systems, and so on? Okay, so explainability is probably the simplest notion to kind of formalize in this case, because it's pretty much very clear from the initial problem we asked, right? What happens when there is a mismatch in expectations, right? The system is coming up with a decision, the human is coming up with a decision. And the problem is you disagree in the decisions, right? You thought the agent should have done something else, and the agent is doing something else. So you, in some sense, want to make sense of why is the agent trying to do this. So explanation is all about resolving this disagreement, okay? So again, going back to those three dimensions, we can see that the first two dimensions, in some sense, relates to what we're causing these disagreements to begin with. If there's a difference in knowledge, right? If there's a difference in what I know versus what my system knows, there could be disagreements in, like what we think the right course of action is, right? If I didn't know that there was some bridge that collapsed, right? And the system is trying to say, avoid that bridge, right? If I didn't know that the bridge was no longer there, I would be confused why the system is trying to avoid what I thought was the closest, the shortest path. Then there is a difference in inferential capabilities. I'll mostly focus on cases here where humans are more limited in their inferential capabilities, and the system is able to come up with, policies that might, or behavior that might seem like it's suboptimal or confusing to the human. But that's not the only case. There could be cases where people are much better equipped to, solve the problem. So again, inferential capabilities should be straightforward in that, I couldn't think hard enough about the problem to come up with the best solution. But the system could take into account all the considerations, all the constraints, all the preferences, and come up with a solution. I just didn't think about it much. And vocabulary is more about, at the end of the day, if I'm giving explanations, it has to be in terms that the people understand. Like the user, it has to be in terms of concepts and ideas that the user can make sense of, and not in terms that the system itself might be reasoning about. And that's what I mean by vocabulary mismatch. And we'll see how that can be resolved. Okay, I'll try to kind of quickly go through some of the work I've done in this space, because it kind of informs this kind of solutions we could have. The first set of work I've done was in terms of explanations which will handle this knowledge asymmetry. So the problem is simple. You have two models and they're just different, right? Humans' knowledge is different from or humans' beliefs are different from what the robot's knowledge is. That means the course of action each would select is different. So the solution seems simple enough, right? You resolve that asymmetry. You tell the human what they did not know before, right? So the technical challenge here is you don't want to dump the entire model to the human. You want to figure out what parts of the model to communicate. And I've looked at this problem in cases where the human's knowledge is known upfront, So this is the nice case where you can prove a lot of things and it's very clean. You just figure out, okay, given this is the human model, what's the minimal set of information to give? Then I looked at cases where human model is not known upfront, but you have some information about the human model. So instead of a single model, you have now a set of models, right? And now you need to give a set of explanation. So this basically, what happens is from the earlier search over a space of models, now you have a belief space over models. You don't know the exact model, but you have a belief over here are the set of possible models, and you're trying to give a set of explanation. So here you could have solution forms which are similar to things like conformant plans or contingent plans and things like that. So I've looked at those kind of cases. And then you have the case where the human model is not known at all, right? You don't know anything about the human model, and you still want to give the minimal set of information that could help the human. So in this case, rather than going over the set of possible model, you're doing a search over possible set of explanatory messages. Because in this case, at the end of the day, all you're doing is you're providing information about what the robot knows. So the set of explanatory messages is in some sense fixed. And you're trying to figure out what's the minimal set you need to give. And these things can be aided by learned components, which will figure out, okay, from my previous interactions with users of similar background, here is the messages that help and things like that. Okay, so then there is the question of addressing inferential capabilities. There could be cases where even if the human knew exactly what the robot's model was, just because of the complexity, they might not be able to come up with the same solution. So in this case, I've looked at strategies like, you could allow for more interaction in the sense of the user could ask more pointed questions, like, why did you not make this choice? Why is this specific part of the plan? Things like that. And also you could use simpler models. And here simpler models could involve things like state abstraction, local approximation, other forms of problem simplification, like, if you have a numeric planning problem, or if you have a stochastic planning problem, to explain those things, you don't really need to talk in terms of the original problem. You can turn it into a simple classical planning problem and explain it in those terms. So this is what I meant by problem simplification. And problem decomposition is, instead of talking about the entire planning problem, you could break it up into smaller horizons. You can talk about explaining with respect to a subcode and things like that. To concretize that a bit, think about this case where you have a rover in Mars, right? Rover has so many complex sensors, and it's keeping track of so many information. But if you were to ask the rover, why can't you go to this green cell? Most of that information is irrelevant to that specific question. All you need to talk about is the fact that, there are obstacles on its way to the green cell, right? So you've taken a much more complex problem, abstracted out the irrelevant details, and you're explaining against what's a much simpler problem. Now, again, with problem decomposition, rather than talking about, going all the way to the green cell, you can take a much like a sub problem, which is, not only can I not get to this green cell, I can't even get to this red cell at the middle, right? So now you're talking about a much small, like a sub problem of the overall thing. So this is what I mean by problem decomposition. And then there is the question of vocabulary mismatch. So the usual, sorry. So usually in this, this is again the case where, let's say the AI system, right, might be reasoning or representing its world in terms that is completely inscrutable to the human. One example might be you might be using a neural network, right? You might be using an RL agent that uses some kind of neural network-based approximation. It's representing its world in terms of vectors in high-dimensional space. People don't do that, right? People think about the world in terms of objects, relationship between objects, right? High-level concepts. So you can't just give explanation in the vector space. That won't make sense to the user. So what we can do is we can take the problem that the system was trying to make sense of and convert it into symbolic representation. For example, for me, that meant converting it into a PDDL problem and using that PDDL problem as the basis for giving postdoc explanation. And the PDDL problem would be represented in terms of the concept the users know. So for example, this is a case where, this is a famous Atari game called Montezuma's Revenge. It's a game where there is like a much more, longer horizon reasoning, right? So rather than giving using some kind of explanations like what would be considered more popular forms of explanations where, if you ask a question like, why did you not pass through the skull? Something the AI, like more, neural network based explanation would be, they might highlight regions in the image and say, oh, because of this region, I couldn't do it. That doesn't make sense, right? Why is that region the more important one? But instead, we can build a PDDL model that might approximate the dynamics around here. And it could be built on terms of concept or propositions which make sense to the user, like, the agent is on the ground, there may be there is a skull next to it and stuff like that. And talk about the fact that moving left has a precondition that the path is clear. So I can't do the action move left there. So this is a case where we've taken something that was harder to make sense of and converted into symbolic form. So I won't go into the details of how these models are built, but it usually takes the form of this sampling-based algorithm where you are querying a simulator and trying to build these models. One thing I want to talk about in the context of post-hoc explanation is there's always a problem with post-hoc explanation that you're just, in some sense, like getting into this problem of you're like feeding into confirmation biases because you are building this explanation that the user wants to hear, and that might build into their biases and stuff like that. So in the paper, we also have additional mechanisms to make sure that we can give guarantees on this is exactly the reason why the system avoided the action that you wanted to query about. So that's a point that has to be taken into account when we are building these post-hoc explanation. Okay, so explanation is one way of solving this problem of mismatch. The other way is design. You can do environment design so that you do by default get behavior that are going to be interpretable. Again, I won't go into too much details over here, but this was the case where the user originally expected the robot to go through that path, but the robot's optimal path is, the one highlighted in red. So you can actually build the environment so that seems like the natural way for the robot to act. Okay, now coming up to advisability. What I mean by advisability is the system need to be capable of taking interpretation and making sense of it, or correctly, taking instructions and being able to interpret it correctly and the way that the user would have meant it. And a more concrete problem of advisability is what's called as a value alignment. Again, I want to give a bit of a disclaimer here that value alignment is a very loaded term. For different people, value alignment means different things. And so based on the community, it means value alignment might be interpreted differently. The one that I go with is something that was championed by Stuart Russell in the sense of value alignment is ensuring that, the objective that the system is maximizing for is what the user intended, right? In some sense, when the user provides an objective specification or an instruction, they had an underlying intent. They wanted the system to do something. And the job of a value alignment algorithm is to make sure that the system is going to act in the way that aligns with the intent of the user. Okay? So in some sense, what I want to do is I want to revisit value alignment through the lens of human-aware AI. And what is going on? Why does this value misalignment problem arise in the first place? So this is how I envision the problem arising. So you have a mental model for the system. The user has a mental model for the system. They have some desired property that they want the system to satisfy. Well, let's call that property sigma h. The user is trying to figure out, how do I change the system's model so that any behavior it generates is going to satisfy that property. So they're trying to reconstruct this instruction based on what they want to see in the world. Okay? So they're going to start with their original beliefs about the world. They're going to figure out what to change. So this change could be in the form of giving a new goal, giving a new reward function, adding constraint, adding preferences. But at the end, what they want to see is a system, like exhibiting certain behavior. So one of the question is, the instructions are never direct encoding of the properties they want to see in the world. Because in most cases, the property might be too complex for them to directly, specify. And in some cases, it might also be implicit. People might not have thought about what they don't want to see until they are shown that. Right? They might have some vague ideas of what they want to see, and they provide this instruction. Okay, so again, once we think about the process of providing objectives and instruction in this slide, you can clearly see where this misspecification could arise from. For one, the fact that the human is relying on their estimate of what the robot model is to come up with this instruction could be a source of misspecification, right? They might just be wrong. And they might they might not know what the robot's model is like. They might just give instructions that, leads to issues. Inferential capabilities, right? This could be a problem because they just didn't think about some ways the robot could have acted based on that instruction, and that could lead to issues. Then there is a question of vocabulary, right? They give certain objectives based on some symbolic representation, and how the system grounds it could be extremely different. So just to give you guys a sense of how these misspecifications could play out, let's look at an extremely simple case. What would be considered the starting point for most of these problems, which is, let's look at deterministic goal-directed planning problems. So what we would consider classical planning problem, right? We know the human model, so we know what the human thinks the robot's like what humans believe about the robot is. Instruction is the goal specification, whatever the human asks the robot to achieve. And what's more, let's say the human specifies what plan the robot should follow. And sigma h corresponds to some true goal specification, right? When I mean by true goal specification and the original goal specification is, there might be some mismatch there, right? The true goal specification might involve avoiding some side effects that the human doesn't want to see, or you might have some extra requirements that the human never specified. Just to kind of ground this problem, let's think about the case where this is an example I like to use, in that the human says, ask the robot to make tea. What's left out from that specification is the fact that maybe the human doesn't just want tea, but wants tea to be made using some good quality tea leaves or something like that. Okay? And then there is a shelf with what looks like a milk jug, but that's the best icon I could find. But let's just assume that this is like some jars with tea leaves. And there is one jar on the bottom which contains low quality tea leaves, and the one jar on the top which contains high quality tea leaves. And the human says, okay, this is how you do it, right? You move the box towards the shelf, get on top of the box, and pick up the high quality tea leaves. Okay, so that's what's given to us. So this is like the extremely simple setting, right? Everything is given to you. There is nothing left out. But what happens is, here's one potential solution. Why don't you just execute the human plan? But the problem is the plan is coming from a different model. The plan that the human gives may not be even be executable. For example, the robot may not be capable of getting on top of the box. That's something the robot can't do because the human has an incorrect model. So even if it's executable, there's no guarantee that what the robot end up achieving following this plan would match like anything of what the human was expecting. Again, because the plan is coming from and is evaluated in a different model. So here is a different solution, right? You know what? Let's not follow the plan. Let's just figure out what the human thought will happen if you follow the plan. Let's try to achieve it. Again, this is not possible because robot's model is different and you might not be able to achieve the exact same end state, right? So what can we do? What we can do is look at the plan and figure out of the end goal state, what were intended by the human and what were the side effects. So in fact, in this is a paper we presented at AAI. We can look at the human model and figure out, which of the end goal state were actually just accidental. And so we can actually modify existing goal recognition algorithms to figure out if I were to change any of the fluence in goal state, how much of a difference does it make in my plan? Does it make my plan easier? Then it means that must have been important because I went out of my way to achieve it, right? So that's the kind of intuitions we can use to make sense of what goal facts actually were important to the user. And once we have that information, we can use methods like value of information to figure out, what questions do I ask about what was important to the user and what were not, okay? So I've been told we might be running a little bit behind. So I'll try to speed up a bit, okay? So again, the takeaway here is what seems like a seemingly simple setting. Once we start introducing the complexity of this mismatch, you start getting much more richer problems, much more, it's not as straightforward as you think you would, it originally looks like. The other thing is, so I won't go into a lot of details here. One of the interesting part is once we start adding in this framework, you also start seeing faults with existing methods. For example, let's look at a simple MDP setting, one where what the human wants is they want the robot to visit one of these green states. It doesn't matter which one. They want to visit one of these states, and you want to avoid this red state. So in some sense, the human gives some reward function. The reward function may not be correct, right? Because the human made the reward function based on their beliefs and stuff like that. What the state of the art, or let's say what the popular way of doing this would be, they would say, look, don't take the reward on the face value. Just assume there is this some unknown human reward function and try to figure out what this unknown human reward function is. Right? So take the reward function as an observation of this underlying actual reward function. What we were able to show, I won't go to the counter example, but what we were able to show that is, in some sense, if you were starting with the fact that there is a behavior, should not be. There is a behavior, and the reward function is some way of telling the robot to generate certain behavior. We can show that there are cases where there exists no single reward function, which will result in the same behavior in the human and robot model. So that means these earlier ways of figuring out what the true reward function is a dead end, in the sense that you can never generate a single reward function that the human would agree on, that this is the reward function, because that reward function would never generate the behavior in the human model. And it's any reward in the human model that would generate the behavior that will never, which will generate the behavior in the human model, will never generate the behavior in the robot model. So the human and the robot will never agree on a single reward function. So all this existing method of figuring out the true reward function will never work out. But instead, what we need to do is we have to query the human about what did the human expect? What were the behaviors they expected? And try to recreate those behaviors. So we shouldn't be querying about rewards, but we should be querying about what their true intents was, like in terms of what behaviors they want. Again, so, this is the big takeaway that is, when we have instructions, you should be asking about what was the intent behind those instructions. And we also did some work on the same thing about instructions should be specified in terms that the human knows. So that means in this case, instruction should be providing symbolic, um, uh, through symbolic means, like things like PDDL and stuff like that, which might be incomplete in some sense, but you should be taking those instructions and try to incorporate it into the agent's decision-making algorithm. Okay, so this is actually a part I won't talk about because there's a talk coming up about this part, so I will skip that for now. But it's again connects to the fact that environment design could be a useful way of generating value-aligned behaviors. Okay, so how much time do we have? 10 minutes. Okay, I'll try to speed through these slides in that this might be a lot, but again, trust can be formalized in these human-aware AI terms, in that trust is always context specific. So when you're asking about trust, it's with respect to a certain aspect of the behavior. So what we'll call contracts. So trust here can be formalized in terms of the likelihood that the agent will, satisfy certain contracts. Contracts here could be about certain performance, it could be about certain kind of behaviors and stuff like that. Again, and trustworthiness is about the question of, do humans perceived likelihood of the agent achieving something is the same as the actual probability of the agent achieving it. So that's what a trustworthiness and trust calibration is all about. You're trying to, in some sense, align those different probabilities. And again, we can talk about these the dimensions, even in that context. One quick thing I do want to highlight is, in terms of trust, there's a huge gap in how the human factors people talk about trust and how the AI people talk about trust, or in terms of explanations trying to boost trust. In that, most of our explanation work is focused on this aspect called performance or capabilities. We are always trying to explain why the AI system is capable of something. But an equally important aspect of trust is what's called as purpose. What is the intent of the agent or the intent of the designer of the system? There isn't really any explanation mechanism for dealing with that. Because even if I said, the intent of the system is to help you, why should you trust me, right? I could just be lying. So those kind of aspects haven't really been looked at in the context of explanation. Then there is the assistance problem where, you can look at these asymmetries to figure out when the user might be heading for a failure. Again, you can leverage things like goal recognition to figure out, is the human likely to fail at their task, and then try to provide assistance. And then there is also the question of deception. Deception can again be talked about in these terms, because you can leverage the fact that there's an asymmetry between the attacker and the defender to actively deceive the person. So this is the work we did last year, where hidden defender. So this was trying to replicate things like honeypot. Defender was masking its actions using the non-determinism of the world. So in some sense, it was actively trying to hide the things. Okay, I'll try to wrap it up now. I want to thank all my collaborators. This was not done in isolation. One of my collaborators has walked in. So yeah. So that's the conclusion. Hopefully we do have some time left for questions and stuff like that. So thank you again so much for the invitation.
Thank you.
Thanks for the talk. Thanks for the talk, I really enjoyed it. So you made a statement saying that we can always show that there are no reward policies that leads to optimal solutions in what the robot thinks and what the human thinks. I was wondering, do you show that like theoretically? And
Yes.
if so, how do you formalize that?
So basically, we showed it using a counterexample. Basically, we built a counter example where you can see that, like more than that, think about this intuition, right? A behavior is the result of both the reward function and the transition function, right? If you think about behaviors like, like a policy trying to maximize the reward function, it's dependent on the transition function. The transition function could be different from the human model and the robot model. If it's different enough, you can ensure that the same reward function will never result in the behavior you want.
Do you have a parameter that says
No.
if they are this different, it's sufficient?
No, we haven't, in some sense, quantified the difference. We were just showing the existence of a case where you can't build a code. Right? Yes.
Sorry, at the beginning, you mentioned that there's a difference between the knowledge of the human robot. This addresses that, and you focus a lot on when the human doesn't have the knowledge that the robot has.
Yes.
And you mentioned that you
Yes.
can handle also the other side, but
Yes.
I didn't really see how
Yes.
you go in.
Yes. So one of the works where I did handle it were cases where the human can just push back. So this is partly a philosophical question of how should you explain something. So most of the cases where I've handled, and in general, more of my mature work is in the context of explanations. One of the things I've always believed is if you're explaining something, you should be explaining it from your point of view. So you're always explaining as if what you understand about the world. You're providing explanations there. The human always has the choice of pushing back. So the human would say, no, you are incorrect about it. Then you get into questions about things like, who's right? Who has the latest information? So, it gets into questions like, what sources of information are there and stuff like that. So I haven't handled those kind of questions of, like, in some sense, there's a negotiation which you need to resolve these things. I haven't gotten to there, but I have looked at cases where human can override the system by saying, you're wrong about this fact. Then you get into a new dialogue where saying, look, even if that fact is not true, here is another explanation, and you can go through that the dialogue. Yes. No.
Interesting. When you're talking about explainability and mention like post-hoc explanation.
Yes. Yes.
I was interested because you mentioned confirmation.
Yes.
So I was just wondering a little bit how it was included and if there are other like types of biases.
Yes. So the reason confirmation bias is particularly bad in this case is because you're taking the concepts from the user. In some sense, what was happening is the user is saying, here are the relevant things. Then go find me an explanation. By the very fact that the user is giving you those concepts, you're trying to find an explanation in those terms. So you could be really feeding into what the human thinks is the right explanation. The way that we've tried to avoid it, and usually how people have avoided it in other works also, is providing some statistical property that this explanation holds in the true simulator. So our explanations were in terms of preconditions. A lot of the times you'll say, oh, your plan that you wanted to do won't hold because there's a precondition that avoids it. So in this case, the precondition was, you can only move left. That's what the robot says, the human says, is instead of jumping over the skull, just move left. So there's a precondition that says move left is like, you can only move left if the cell on, like, in front of you or on the left of you is clear. Okay. So here, that's a case where in terms of giving guarantees, what we would do is we are going to estimate that that explanation in some sense holds in the simulator. So we are going to try to generate a lot of, different traces and try to build some kind of probabilistic guarantee. Because here the problem is, even though we haven't found a counterexample, there's always a likelihood that we didn't sample enough. So we can, in some sense, quantify how confident we are that this explanation holds, right? So, and there is a different problem that any concepts we learn, it's going to be very probabilistic. So there is a problem that the classifier said that, the cell is left when it's not. The cell is clear when it's not, right? So we also have to quantify that into our explanation. So the possibility that the symbols itself, we are misinterpreting it. So we have to take in that account. So the way we handled it is in terms of conferences. I'll be the first one to agree that that's probably, not the greatest solution, because people are notoriously bad at understanding probabilities. As soon as you slap a number next to it, people are very happy to take it. But that was like the first step towards something. We do hope to further build on it. Yes. Oh, okay.